in chemical reactions, you're starting with the reactants and you end up with products. The atoms and electrons in the reactants rearrange themselves and create new materials, new chemicals in the form of products. On paper, the balanced chemical equation can show all of this perfectly, how 2 molecules of this and 1 molecule of that will form 3 molecules of this other thing. And that works on paper, but in practice and in a lab setting, it's a little difficult to do that. In a balanced chemical reaction, it's focusing on moles and moles or molecules that undergo these reactions. But in a lab, it's incredibly difficult to actually measure down to the molecular level about how much exactly you would have in order to react perfectly. And that's where the concept of a limiting reactant comes in. A limiting reactant is one of those reactants that dictates how the reaction happens or how far along the reaction can go. The limiting reactant is something that would be used up first, and the other reactant that's there would be left over. So when you're going through and looking at the limiting reactant, it's the reagent or that initial reactant that there is less of it there. It can perform fewer reactions for the limiting reactant than the excess one. And this experiment looks at how to determine the limiting reactant, both in theoretical ways and calculations to determine the limiting reactant based on the sheer number of moles that are available in a situation. And the experiment itself also looks at determining the limiting reactant based on experimental observations, looking to see, based on experiments, what is the limiting reactant. In a lab setting, the limiting reactant is something that controls when the reaction is finished. The limiting reactant is of multiple reactants, the one that will get used up first. And once it's used up and gone, the reaction can no longer progress because that reactant is now gone. All of the other reactants will still be there and remain in excess. And this experiment looks at preparing different combinations and trying to decide what is the limiting reactant and how much of it was there, how much of the excess reactant was left over. So in a chemical reaction, there are both products and reactants. And the reactant is the starting material, and this is where the limiting reactant would be. It's the materials that rearrange themselves to generate something else. And that something else is the product, the end result. Most times in chemical reactions, the reactants appear on the left and the products appear on the right with an arrow in between pointing to the direction, going from reactants to the products. Now, there are a lot of different types of reactions. Some can be one reactant just rearranging and going into one product, one reactant splitting apart into 2 products, 2 reactants combining into 1 product, or a number of different ways that these things can react. And in a lab setting, you can't get these amounts down to the actual molecule. You can only deal with what you have in front of you, and that's weighing things out on a scale or a balance, or looking at volumes and masses. And it's very, very difficult to have them exact to match up with a perfectly balanced equation. So in these real world situations, there will always be something that's not quite enough. There's not quite enough of something to fully react with everything else, and that would be the limiting reactant. So in a balanced chemical equation, something like this, you have, in this example, calcium chloride reacting with 2 sodium hydroxides as the reactants to give 1 calcium hydroxide solid and 2 sodium chlorides. These are the products. In this balanced chemical equation, you have 1 mole of calcium chloride plus 2 moles of sodium hydroxide to give 1 mole of calcium hydroxide and 2 moles of sodium chloride. How that would look in terms of the actual mass is if exactly 110.98 grams of calcium chloride reacts with 79.99 grams of sodium hydroxide, that will give the products of exactly 74.09 grams of calcium hydroxide and 116.88 grams of sodium chloride. But weighing out these exact masses can be tricky because there can be variability. These are also based on truncated atomic weights. So the actual down to the molecule would be farther out and have a greater level of significance. So in labs, one of these is going to be limiting based on the actual amounts that you weigh out. And in these reactions, the limiting reagent or the limiting reactant is what is controlling the entire chemical reaction. Because whatever excess material might be there is not going to be involved in the reaction. Only what can react with the limiting reactant is what will generate the product. So when going through and looking at chemical equations and calculating final mass of product or final moles of either reactant product, it's all based on the limiting reactant because that is the one part of the reaction that is controlling the rest of the reaction. In sticking with the same reaction that we looked at a couple of slides ago, the reaction of calcium chloride and sodium hydroxide, a much more relevant thing in a lab setting would be to weigh out some amount. So if exactly 50 grams of each was weighed out and combined, what would be the amount of products that would be generated? And what would be the limiting reactant? And to determine the limiting reactant, you first have to see how many moles of material you have. Chemistry is performed in moles, but the actual action in lab is weighed out in grams. So there's always going to be this conversion between grams and moles. A good rule of thumb, if you're ever given anything in a question, in a problem in grams, convert that to moles because that is what's going to be used in any sort of chemical equations or any sort of chemistry. So first off, if we have 50 grams of both calcium chloride and sodium hydroxide, the first thing we're doing is figuring out how many moles this happens to be. So you're dividing the mass by the molecular weight, and that's going to give the amount of moles of each material. So in the case of calcium chloride, we have 0.4505 moles. And with sodium hydroxide, there is 1.250 moles. Many times, especially in general chemistry, you might not be dealing exactly with weighing out the material directly, but you might be dealing with solutions of materials. So they have a specific molarity, and you're measuring out the volumes instead of the mass. The molarity, again, is a concentration. It's the amount of moles that are present within 1 liter of the solution. So with the same example, if 250 milliliters of a 1.802 molar solution of calcium chloride was combined with 500 milliliters of a 2.500 molar sodium hydroxide solution, you still have to go about finding how many moles there are of each component. And to do that, you're looking at the molarity equation. Molarity equals moles over liters. So to find the number of moles, you will multiply both sides by liters, by the volume, and that will equal the number of moles. So the molarity times the volume in liters gives the number of moles. So when we multiply the 1.802 molarity times the 0.250 liters, remember this was milliliters and it needs to be converted to liters, so that would be divided by 1,000. And when we multiply these two together, we get the 0.4505 moles of calcium chloride. And likewise, we get the same, the moles of sodium hydroxide. So in lab settings and in problems, you can either be given the mass directly, and if you're given the mass directly in grams, you can convert that to moles just by using the molecular weight. Or you could be given solutions, and this is a concentration and a volume, and you can calculate the moles from that. Either way, you're looking to find how many moles of starting material do you have for all of the different reactants. Once you have the moles of the different reactants figured out, you can then go through and multiply these by the stoichiometry. That's the balanced equation. Looking at this balanced equation, 1 calcium chloride will generate 1 calcium hydroxide. The ratio between calcium chloride and calcium hydroxide is 1 to 1. So if you have this many moles of calcium chloride and the ratio is 1 over 1, you're multiplying it just by 1. And this would generate 0.4505 moles of calcium hydroxide. Again, because for every 1 mole of calcium chloride, it generates 1 mole of calcium hydroxide. So if you have 0.4505 moles of calcium chloride, that generates 0.4505 moles of calcium hydroxide. They're the same because it's 1 to 1. With the sodium hydroxide, however, the relationship is 2 to 1. It takes 2 sodium hydroxides to react and combine to make 1 calcium hydroxide. So in essence, you're multiplying by the ratio of 1 over 2, or dividing by 2. So if we have a starting number of moles of the sodium hydroxide, 1.250, that will give 1.25 divided by 2, that will give 0.625 moles of calcium hydroxide. So in each case, you can see what the maximum amount of calcium hydroxide to be produced would be. And in this situation,
the calcium chloride produces less. This is the limiting reactant. So an amount of 50 grams of calcium chloride will produce 0.4505 grams of calcium hydroxide, where 50 grams of sodium hydroxide will produce 0.6250 moles of calcium hydroxide. This number is smaller than this number, and that's what dictates the limiting reactant. What is the reactant that will use up everything and fully react until it's gone first? What will generate really the least amount? Because in this case, there's enough calcium chloride to generate 0.4505 moles. And there's enough sodium hydroxide to generate 0.6250. The difference between them is going to be the moles of sodium hydroxide left over. So when you have the limiting reagent, there are a number of things you can determine after that. You can look at how much of the actual product will be formed. If you mix these things together, how much of the end material will actually be generated. That would also be considered the theoretical yield. You can see how much excess reactant remains. So if the limiting reactant is all used up, it's going to react with sodium hydroxide, but how much of that sodium hydroxide is left over? You can calculate that and figure out using the same method as before by multiplying these through by the different ratio. And you can figure out how much more of that limiting reactant can be added into that system. So if there was excess sodium hydroxide, how much calcium chloride can that excess sodium hydroxide react with? There are a lot of things that you can calculate once you have the limiting reactant.
When a reaction occurs, you're taking the reactants, rearranging those atoms and electrons, and creating the products. In this example, there is the two reactants of hydrochloric acid, HCl, and magnesium metal. And when these two things react, they form hydrogen gas and a solution of magnesium chloride. So by mixing these two together, the reaction can progress. And you can see that it's generating the hydrogen gas, it's bubbling, it also generates a lot of heat. And the limiting reactant is the initial reactant that's going to dictate when the reaction stops. When all of the limiting reagent is used up, the reaction can no longer continue because it's gone. That does not mean that everything is gone. There is still some of the other reactant left over, and that other reactant can continue to react if the limiting reagent was added back in. So when going through and calculating different things, if you were to do this based on numbers, numerical values, how many moles of hydrochloric acid was there to start, how many moles of magnesium was there to start, you can figure out what the limiting reagent is, how much of it was there, and how much excess or how much of the other thing was there as well. But experimentally, you can also do that. The reaction is now complete, everything is used up, the limiting reagent is gone. But if there's any excess material, it can still react if the limiting reagent is reintroduced. So if I split this up into two portions, if I add more hydrochloric acid, Nothing happens. There is no further reaction. So that means that there is no magnesium left in this reaction mixture for the hydrochloric acid to react with. However, if I add a little more magnesium, the reaction continues on. That means that there was still hydrochloric acid remaining. Hydrochloric acid was in excess. So the limiting reagent in that first reaction in the larger beaker was the magnesium. The reagent in excess was the hydrochloric acid. And by knowing exactly how many moles of starting material you have, you can figure out how many moles of actual product you're generating, and therefore how many moles of excess reagent is still there after the reaction. And you could figure out in a lab setting how much more limiting reagent do you need to mix into there for absolutely everything to be fully reactant and the reaction to be completed.
So you can generate a lot of different numbers and calculations once you have that limiting reactant determined. So one of the things you can calculate is how much product is formed. What is the mass of that solid, this calcium hydroxide? How much of that will there be when you combine 50 grams of calcium chloride and 50 grams of sodium hydroxide? You're trying to figure out what is the mass of that solid. So once you have the limiting reactant, you can see how many moles of product it will form. So in this case, you have 0.4505 moles of calcium hydroxide. And then using the molecular mass, you can convert moles back into grams. So in this example, when you combine 50 grams of calcium chloride and 50 grams of sodium hydroxide, you will end up with a total product of 33.38 grams of calcium hydroxide as a solid product. The other thing you can do is how much of that excess reactant is remaining. So again, this is all based on the limiting reactant. That's the starting point for these calculations. You have to determine what is the limiting reactant first. So in this case, the limiting reactant was the calcium chloride. And there is 0.4505 moles of calcium chloride. When you multiply this out by the ratio, for every 1 mole of calcium chloride, it will react with 2 moles of sodium hydroxide. And you're trying to cancel out this moles of calcium chloride, so that's going on the bottom. So you're multiplying it by 2. So 0.4505 moles of calcium chloride will react with twice as much sodium hydroxide. So that will react with 0.9010 moles of sodium hydroxide. So when you take that, multiply it by the molecular weight, you get how many grams of the sodium hydroxide actually reacted. And you can take this then, if you start it with 50 grams total and 36.04 grams of sodium hydroxide reactant, then there is 13.69 grams of sodium hydroxide remaining that still can react, but it's leftovers. You can also do it just based on the moles. You had a if you already converted the 50 grams into moles, you had 1.250 moles of sodium hydroxide and 0.9010 moles reacted. So you're left with 0.3490 moles of sodium hydroxide that is left over and can still react. And kind of more of the last step is how much more limiting reactant is needed. So how much excess or how much limiting reactant can this situation handle before everything is gone? So you're figuring out how much is left over. So this excess reactant. You have 0.3490 moles of excess sodium hydroxide. And for every 2 moles of sodium hydroxide, it reacts with 1 mole of calcium chloride. So now, again, to make sure that this sodium hydroxide is canceled out, you're dividing by 2. It's the same ratio, but you're going in the opposite way now. So you're dividing by 2 instead of multiplying. So it will take half as much calcium chloride to react with this. So overall, a total of 0.1745 moles of calcium chloride is needed to fully react with everything of that excess sodium hydroxide. And then if you take that and convert to a mass using the molecular weight, you see that 19.37 grams of calcium chloride is needed. So overall, this reaction would be perfectly balanced in theory if you had 50 grams of sodium hydroxide and reacted 50 plus 19.37 grams of calcium chloride. Then it will react in these same ratios. But weighing things out in a lab doesn't always fall to that exact measurement. And that's why the limiting reactant is something that plays a major role in determining how much of the actual product is formed and what you can do with the remaining reaction. So in the reaction itself, there was the calcium chloride and the sodium hydroxide that was giving way to calcium hydroxide and sodium chloride. You notice that all of these have had a phase on them. The calcium hydroxide ends up being a solid, but I listed all of the other samples as aqueous. That means dissolved in water. And when you're taking an ionic solid and you're dissolving it in water, it's breaking apart into the individual ions. So an aqueous solution of calcium chloride would break apart into 1 calcium ion and 2 chloride ions. 2 sodium hydroxide compounds would break apart into 2 sodium ions and 2 hydroxide ions. The calcium hydroxide, again, is just a solid, so that's still going to be a solid. It does not dissolve. And the sodium chloride will break apart into 2 sodium ions and 2 chloride ions. So when you look at this, you'll notice that these 2 sodium ions appear on both sides of the equation. And the 2 chloride ions also appear on both sides of the equation. This equation right here is the full ionic reaction. Every single ion is taken into account and written out. And when you're looking at these, when you find something that's on both the reactant side and the product side, there's no change in the amounts or anything, that is a spectator ion. It did not participate in the reaction at all. So these, in this case, chloride ions and sodium ions did nothing. They were spectators. They looked on as the calcium ion and the 2 hydroxide ions are the ones that actually reacted and formed the calcium hydroxide solid. So while this is the full ionic equation when everything is broken apart, the net ionic equation would be just the reactants. So in their ionic form, the net ionic equation would be calcium ion plus 2 hydroxide ions to give 1 calcium hydroxide solid. And in future experiments, we'll go over in more detail of breaking apart these full reactions into full ionic equations and then net ionic equations. But right now, we're looking at just what is a spectator and what is the actual reactant when we're looking at overall what ions are present in these solutions and which ones are actually forming a reaction.
In the experiment itself, you're going to be looking at determining these limiting reactants. You'll experimentally determine through a qualitative method what is the limiting reactant over a number of different reactions using different chemical tests. You'll also look at things quantitatively, determining how much of that limiting reactant is there and how much of the final product is generated, looking at the theoretical yield. In the first few reactions, you're going to be looking at precipitation reactions. And these are reactions where you have 2 liquid solutions, and when they're mixed together, it forms a solid. And when this solid is formed, it's based on the solubility. The solubility of the product itself is what dictates if it's a solid or if it stays as an aqueous solution, as its individual ions. When you look at a chemical reaction, you can determine the different products. Using the different reactants, you can determine what the products of the reaction will be, but what is the phase of those products? Are they solid products or are they aqueous? And what determines that is the solubility. And when one of those products is at a concentration above that solubility limit, then it causes precipitation. That it's over the solubility limits, so anything above that exists as the solid in solution. In part B of the experiment, you're focusing on precipitation reactions. And you have seen precipitation reactions in a number of the experiments before. And a precipitation reaction is where you have 2 completely clear liquids, and when you mix them together, it forms a solid. And this is not a full chunk of a solid. This is particulate that's dispersed through a solution. Now, anytime you really can't see through the solution, if a solution is cloudy, that is an indication that there is precipitate that is in that liquid. One good example that you've probably seen before is milk. Milk, you cannot see through. It's very, very cloudy. And the reason for that is the small particles of protein and fat. That's a precipitate. It's a solid, and it's suspended throughout the liquid. So that is a precipitate. If you were to leave milk sit for a very long time, you would see it even start to settle. I would not recommend that. But in other reactions, you'll be able to see the precipitate settle out to the bottom initially before too long. And in this reaction, in part B, you're looking at a few different precipitation reactions, and you're going to be separating the precipitate, the solid material, from the liquid material using filter paper?
So in this first part of the experiment, you're going to be looking at 3 different precipitation reactions, all involving calcium chloride. The first 2 of these reactions are purely qualitative. Through the experiment, you're determining what is the limiting reactant. And you're going to be combining calcium carbonate solution with unknown solutions of sodium carbonate in the first reaction and sodium phosphate in the second reaction. Based on what the reactants are, you can determine what the products will be. And from the solubility of those 2 products, you can determine what is the solid that actually forms. And in the secondary test in lab, you can determine what is the limiting reactant. Is it the calcium chloride, or is it the unknown, either sodium carbonate in reaction 1 or sodium phosphate in reaction 2? The third reaction works just the same way. You're going to be combining calcium chloride with sodium hydroxide or potassium hydroxide, depending on what the unknown is. And you can see the reaction happening, just like in these first 2 reactions. However, the unknown itself also lists a concentration of the hydroxide. So you'll know the concentration of calcium chloride and the concentration of the hydroxide, the sodium or potassium hydroxide. In lab, you can go through the same method of determining experimentally what is the limiting reactant, but using those concentrations and the volumes themselves that you're using, you can determine how many moles of that limiting reactant did you have to start with. And from those moles of limiting reactant, you can then calculate how many moles of the solid product is there, the calcium hydroxide, and that would be the theoretical yield of the reaction. In this first part of the experiment, you're looking at these precipitation reactions. And the first 2 reactions are purely qualitative. What is the limiting reactant? And that's really all you're getting at. What is the limiting reactant? In lab, you're going to be taking 5 milliliters of calcium chloride solution, adding that to a test tube, and then 5 milliliters of your unknown. You'll combine those together, and that will form a precipitate. Once you have the precipitate formed and you have the solution, you'll pour that whole mixture into the filter paper and allow the solid to remain in the filter paper and the liquid to pass through the filter paper itself. The liquid contains all of the unreacted ions. And once you have that liquid, you can split it in 2 separate test tubes and perform a second test. To one test tube, you would add additional calcium chloride, and to the other test tube, you would add additional carbonate. Whichever compound causes more precipitate in that second step, that is the limiting reactant in the first step. So for both reactions 1 and 2, you're doing just that, determining what is the limiting reactant. In the third reaction, though, not only are you determining what the limiting reactant is, but you're determining how much of the limiting reactant is there. And this is a quantitative test. You're determining a number, an amount. And when you go through that secondary test, just like those first 2 reactions, you'll determine what the limiting reactant is. But since you will know the specific concentrations and volumes, you can determine how many moles of the limiting reactant there is. From the moles of limiting reactant and the stoichiometric ratio of the balanced chemical equation, you can determine how many moles of product that is generated, and that would be the theoretical yield. The mass of that product would be the theoretical yield of the reaction, the maximum amount of solid that could be produced. But as mentioned, these solids only exist as solid because of the solubility. Everything has some sort of a solubility associated with it, even these, the precipitate, the calcium hydroxide in this reaction. So when you go through this reaction, you can determine what is the mass of the calcium hydroxide product, but also how much of that mass, how much of that theoretical yield is actually there, because some of it does dissolve. Look at the units of what the solubility is for calcium hydroxide and determine how much of that calcium hydroxide could dissolve in your setup, and you would be subtracting that from the total maximum amount of solid itself, that theoretical yield. So in all three of these first reactions, you're combining them, they're forming a precipitate, and then you're passing that mixture through filter paper. And filter paper is, and utilizing filter paper is a lab technique that's used a lot in different chemistry labs. In general chemistry, it's used a lot in organic chemistry and analytical chemistry, as well as a number of other different lab settings. Filter paper is really just like coffee filters. And when you have a piece of filter paper, you can pour a mixture of both solid and liquid in the top of the filter paper. The solid will remain inside the filter paper and the liquid will pass through. Any dissolved ions will also be able to pass through that filter paper and will be inside the liquid that comes out the bottom. The liquid that comes out of the filter paper is called the filtrate. Now, there are a few different types of filter paper. In the lab, you're going to be working with gravity filtration, which is just a circle of filter paper placed in a funnel, and you're allowing the gravity to pull the liquid through the filter paper. There are also different types of filter paper that use specialized funnels and vacuum systems in order to pull the liquid out faster or have it pull through thicker or more precise filter papers.
In a lab setting, one of the very important techniques when dealing with precipitation or recrystallization reactions is how to filter off the solid and the liquid. And many times this is done through the use of filter paper, very similar to coffee filters at home. There are two basic types of filtration using filter paper: gravity filtration and vacuum filtration. In both instances, the filter paper is provided in circular sheets. The difference between the sheets and how fast the filtrate can pass through it depends on the pore size and the packing of the filter paper itself. How tightly woven are the individual fibers and how thick is it? These two properties will dictate whether the liquid will pass through it very fast and leave behind some of the particulate matter that will go through, or will it pass very slow but make sure that all of the solid and all of the particulate matter is captured by the filter paper and left behind. In these two techniques, you can see the difference between gravity filtration and vacuum filtration. The more basic filtration technique with filter paper is gravity filtration. With gravity filtration, a larger circle of filter paper is folded in half into a semicircle, and then the semicircle is folded in half again. What this ends up making is two separate lobes which could be opened up into a paper funnel. This paper funnel is then placed into a regular funnel, and the solution that needs filtration is passed through it. It's called gravity filtration because the only means to draw the liquid through is by gravity. The liquid that passes through the filter paper into the container below is called the filtrate. There are different grades of filter paper, as I mentioned, and sometimes it is necessary for analytical and very accurate filtration to pass the filtrate through a number of different steps of filter paper. Typically, this is good for most types of preparatory techniques where you need to filter out large pieces or larger precipitates, and the filtrate below can then be analyzed. Likewise, the precipitate on top could also be analyzed, and in future laboratory courses, the precipitate on top may also need to be washed with water to make sure all of the liquid is gone and only the solid, the clean solid, remains on top. The second type of filtration using filter paper is through vacuum filtration. In vacuum filtration, the filter paper itself is generally smaller and not folded and stays a whole circle. These circles of filter paper are then used with a special type of funnel called a Buchner funnel. This funnel has straight sides on it and acts like a container. Inside is filled with a number of small holes. This holds the filter paper so it doesn't pass all the way through. It's placed onto a container that is connected to a vacuum system. The circle of filter paper can then be placed inside, the vacuum system turned on, and the solution poured through. Vacuum filtration is a much faster form of filtration. However, the special use of the Buchner funnel and the capability of pulling a vacuum on a glass container such as this is required. In many types of lab settings, a vacuum filtration would be used to more accurately collect the solid, where the gravity filtration will be used more so to look at the filtrate or the liquid passing below. As with the gravity filtration, once the solution is passed all the way through and the precipitate is remaining on top of the filter paper, it can then still be washed to make sure that the precipitate is clean. After the filtration, all of the solid remains on the top, and you can turn off the vacuum system and take the filter paper out and analyze the solid product on top. Being able to filter and separate out the solid component from the liquid component is a very important lab technique that's useful both in general chemistry, organic chemistry, and in more advanced chemistry courses. In the second part of the experiment, you're shown the gravity filtration technique on two separate reactions. To the filtrate, which is the liquid that passes through the filter paper, two additional tests are performed. Each of the original reactants is added to separate portions of the filtrate solution. Whichever reactant causes a precipitation reaction in that second set of reactions on the filtrate, that would be an indication that it is a limiting reactant in the first setup.
So in the reaction itself, for all of these precipitation reactions in part A, you're combining them together. You're taking, for each one of these three reactions, you're mixing 5 milliliters of calcium chloride solution with 5 milliliters of your unknown for each of those three reactions. Once you have that mixture, you're passing it through a piece of filter paper and you're collecting that liquid that comes out of the other side, that passes through the filter paper, that filtrate. To that liquid, the filtrate, you're going to separate that into two different test tubes. To one test tube, you would add additional calcium chloride. And to the other test tube, you would add additional either sodium hydroxide, sodium phosphate, or sodium carbonate. You're adding additional unknown. And you're looking to see in this second test, which solution causes more precipitate. So when you're performing that second test, this is a chemical test to determine in that first combination, this 5 milliliters and 5 milliliters, what is the limiting reactant? Is it calcium chloride or is it your unknown solution? So in that secondary test, you're looking at the filtrate. All of the excess ions, all of the unreacted ions are present in that filtrate. The limiting reactant is gone. It is the limiting reactant. It's all used up. So only the excess reagent is still present in this filtrate. If you add additional excess reagent, then nothing would happen. You wouldn't see any precipitate form because the limiting reactant is still gone. So if you see no reaction or no precipitation, that means what you just added is not the limiting reactant. You added more of what's already in that test tube. However, if you add something and you do see that precipitate form, you do see a reaction, that means that those excess ions were instantly able to react with what you just poured in. So what you had just poured in would have been the limiting reactant in that first combination. All three of these reactions are two-step tests. You're looking at the first combination itself, that 5 milliliters of calcium chloride and 5 milliliters of your unknown solution, and that's the reaction. And then you're doing a second chemical test on the reaction. And that second chemical test is what's telling you what is the limiting reactant.
The first part of the experiment looks at 3 different precipitation reactions, all involving calcium chloride. You'll be reacting an unknown of a carbonate and a phosphate, as well as potassium hydroxide, which has a provided concentration. For all 3 of these reactions, you will combine 5 milliliters of your unknown and 5 milliliters of calcium chloride. In each reaction, it will form a white precipitate. This combination of precipitate and the remaining liquid can be filtered using a piece of filter paper and a funnel. It can be placed directly in a second test tube, and the solution can be poured into the filter paper. As the liquid passes through the filter paper, all or most of the precipitate should be contained in the filter paper, and only the clear liquid should be passing through into the test tube. This liquid is the filtrate of the reaction. When a small amount has passed into the first test tube, you can obtain a second test tube and place the funnel inside, allowing additional filtrate into a second test tube. Once you have 2 test tubes with filtrate in it, you can then begin the secondary part of the reaction. To one of the test tubes, you will add a small amount of additional calcium chloride. And to the other test tube, you will add additional amount of your particular unknown. Based on the reactions, you can determine what was the limiting reactant in that first combination. In this case, additional calcium chloride did not give any additional reaction. This means there was no carbonate present in the filtrate, and the calcium chloride could not react. With the addition of extra carbonate unknown, a reaction occurred, meaning there was extra calcium chloride in the filtrate, and when the carbonate was added, the reaction could continue and form the precipitate. In this setup, the carbonate was the limiting reactant. You will continue this and perform the same reaction or same setup with both your carbonate unknown and your phosphate unknown. Both of these are considered qualitative tests. You're determining what is the limiting reactant, and that's all. For the potassium hydroxide unknown, you'll continue and perform the same setup, determining what is the unknown, the calcium chloride or the potassium hydroxide. However, with the potassium hydroxide, you are given a concentration. From the concentration of both the potassium hydroxide and the calcium chloride, you can determine the moles of each present in the initial reaction. Using what you've identified as the limiting reactant, you can determine how many moles of the limiting reactant there is and how many moles of the solid calcium hydroxide would be present in the precipitate. Using that theoretical yield, you can also determine, based on the solubility of calcium hydroxide, what is the actual mass of the powdered material in the bottom of the test tube.
The second part of the experiment looks at other types of reactions. And in these two reactions, reaction 4 and 5, there is no precipitation. You're not looking at precipitate formation, but you're looking at other observations that can indicate a chemical reaction has occurred. In the reaction number 4, you're looking at the formation of gas, carbon dioxide. You're reacting your carbonate unknown with hydrochloric acid, and you're determining what is the limiting reactant. It's still a qualitative test. You're performing the same setup, looking at the reaction, and then performing a chemical test on the reaction to see what is the limiting reactant. And you're doing this one based on your observations of gas formation. You're looking at the bubbles of carbon dioxide that are generated in the reaction. The fifth reaction looks at color intensity. So another observation that comes up when a chemical reaction occurs, or another observation that can be seen, is a color change or the formation of a color. And you'll see that in the reaction of iron nitrate and sodium acetate. They form a very unique complex ion. And these complex ions are still ions. They are aqueous compounds, not a solid. But it has a color associated with it. The iron nitrate is a very, very pale orange, and sodium acetate is colorless. But when they're mixed together, it forms a darker orange material and a darker orange solution. It's a very unique complex because the iron forms a ring with 3 of these irons and 6 of the acetate molecules. Those acetate ions are all surrounding this iron, along with some water molecules that can coordinate and kind of hook on to these 3 irons. So all 3 of these irons have an octahedral shape. It also interacts with water molecules themselves. And in that process, that splitting of the water molecule, there is an oxygen that forms in the center just to stabilize this entire complex. And what you're looking at, this has an intense color. So in the reaction, you're looking at the formation of this intense color. And does it get darker? Does it get lighter in the reaction? So in reaction number 4, again, this is looking at gas formation. You're still going to be taking 5 milliliters of hydrochloric acid and 5 milliliters of your carbonate unknown solution and mixing those together in a test tube. And you'll see the formation of the carbon dioxide gas that will bubble through, and you'll see it. Then once the reaction is done, and I would suggest mixing it around a little bit with your stirring rod just to make sure that everything is completely reacted, you'll split that into 2 different test tubes. To one test tube, you will add additional hydrochloric acid. And to the other test tube, you will add a small amount, a very small amount, a little spatula tip full of solid carbonate material, sodium carbonate. This reaction is with the H+, that acid ion, and carbonate ion. This is the same reaction from that percent composition experiment a couple of weeks ago. So you'll look at this same reaction and see which one causes more carbon dioxide to be formed. If nothing happens, that means the limiting reactant still wasn't there. So you mix those two things together, and then you're performing this secondary test. If there's no reaction or no bubble formation from adding one of those materials, that means it is not the limiting reactant in that 5 milliliter and 5 milliliter combination. If there is a reaction, that means there was excess of the other component. So in this case right here, I added additional hydrochloric acid, nothing happened. That means there was no more carbonate after the reaction was done. When I added additional carbonate to the mixture, then the bubbles form. There was no carbonate left, but there was still hydrochloric acid left. So when I added more carbonate back into the test tube, it forms that carbon dioxide again. You can see those bubbles. And that would be our meaning that the carbonate itself was the limiting reactant. So in your reaction, you're using some acid and your unknown and determining what is the limiting reactant of this combination. Is it hydrochloric acid or is it carbonate?
The next set of reactions in the experiment still is looking at the limiting reactant based on observations. However, in these observations, it is not a precipitate that forms, but something else. The first reaction looks at 0.5 molar hydrochloric acid and your carbonate unknown. You'll be taking 5 milliliters of each solution and combining them in a small test tube. You can see the slight fizz when the reaction occurs. You can then take a portion of your reaction mixture and place that in a second test tube. To the first test tube, you will add additional hydrochloric acid. You can see from the observations that there was no additional bubbling in this setup. To the second test tube, you will add a small amount of solid sodium bicarbonate or baking soda. And you can see that the reaction continues, in this case rather vigorously. You can use these observations to determine what is the limiting reactant in your unknown sample, that first set of reactions. From this setup, since carbonate still reacted, that means initially there was leftover hydrochloric acid. So the carbonate in this setup was the limiting reactant. Adding additional hydrochloric acid did not give any additional observations. There was no reaction in the second set of experiments. That means there was no carbonate left, and additional hydrochloric acid did not cause a reaction. This setup is the same principle as the initial precipitation reactions, only now the observation is the formation of carbon dioxide gas.
In the fifth and final reaction, you're looking at color intensity, or the color change of the reaction. You're combining, again, 5 milliliters of iron nitrate and 5 milliliters of your acetate unknown, and that will form a darker orange color. With that darker orange color, you can, again, just like in reaction number 4, you can split that into 2 different test tubes. And to one, you will add additional iron nitrate. To the other, you will add additional of your acetate unknown. And you're looking at that color intensity. You're looking what happens to the color itself. The product, that iron acetate complex, is this darker orange color. So if more of the limiting reactant was added, it will generate more of this darker material, and the solution itself will become a darker color. If more of the excess reagent is added, you're slowly going to be diluting that color. If the excess reagent is added, there's no more limiting reagent left, so all you're doing is diluting it, and the solution will get a little bit lighter. And you can look at that, look at these color intensities, and determine what is the limiting reactant in this combination based on these color intensities.
The last reaction setup looks at the reaction between iron 3+ ions and acetate ions. As with the previous experiments or the previous reactions, you'll be taking 5 milliliters of iron nitrate solution and your acetate unknown and combining those in a small test tube and recording your observations. You can see the color change that happens when the two are combined. You could use a pipette to mix the two together thoroughly. You'll then take half of this solution and place that into a separate test tube. Now you have the same iron acetate solution in each test tube. To one side, you will add additional iron nitrate and notice any reaction or color change. And to the other side, you will add additional acetate unknown. The darker orange color indicates the formation of the product itself, iron acetate. Looking at these observations, the addition of acetate caused the darker color to appear, while the addition of iron 3+ caused an even slight reduction in the color. From these observations, you should be able to deduce that the acetate itself was the limiting reactant in the first mixture. By adding additional limiting reactant, the reaction can continue and the formation of the dark color will increase. When additional iron nitrate was added, the colored product did not appear, indicating it is not the limiting reactant.
So overall, you're going to be looking at 5 different reactions in the lab. The first 2 reactions are purely qualitative. What is the limiting reactant? You're combining 5 milliliters of calcium chloride and 5 milliliters of your unknown, either a carbonate unknown or a phosphate unknown, and that's forming a precipitate, which you can pass through filter paper and then perform a secondary test. And in that secondary test, whichever solution causes the precipitate to form, that is the limiting reactant. Reaction number 3, you're doing the same exact thing, 5 milliliters each of calcium chloride and your hydroxide unknown, and determining what is the identity of that limiting reactant, performing this secondary test to the filtrate. However, in this reaction, you're looking at it quantitatively. You're looking at the number. How many moles of the limiting reactant is there? You're using the molarity of your limiting reactant and the volume of your limiting reactant. How much of that did you use? In each of these cases, it's 5 milliliters. You're using 5 milliliters of calcium chloride, 5 milliliters of hydroxide, but the concentrations are different. So with that, you can determine how many moles of your limiting reactant is there, how many moles of the solid product that the calcium hydroxide would it form, that theoretical yield, and what is the mass of that calcium hydroxide, and use the solubility, determine how much of that calcium hydroxide is dissolved in your combined 10 milliliters of solution. The fourth reaction is no longer looking at a precipitation, but gas formation. You're looking at bubbling of carbon dioxide. This, again, is a qualitative experiment. You're just looking, what is the limiting reactant? You're combining your same carbonate unknown with some hydrochloric acid, looking at those carbon dioxide bubbles form, and then splitting that solution in half. To one side, you're going to add more hydrochloric acid. To the other side, you're going to add more or additional solid carbonate sample, and determine from those observations what is the limiting reactant. In that secondary test, whichever forms more carbon dioxide was the limiting reactant in that first combination. And in reaction number 5, looking at iron nitrate and sodium acetate, again, combining 5 milliliters of each, only this time you're looking at color intensity. When you combine those solutions, it will form that orange color. And then if you add more of one component, it will get darker. When you add more of that limiting reactant, it will get darker because there is excess of the other thing. So you're going through all 5 of these reactions, really looking at determining what the limiting reactant is and quantifying different moles of reactant, different moles of the limiting reactant, different moles of product, and theoretical yield.